So this time, let's try to derive the Bellman equations with an easier process than before. And so we will not be using the law of total expectations in this video. So we have the state value function expression given over here, where it is simply the expected return given that you start from the state S and you follow the policy pi optimally thereafter. So let's expand this, and given that gt is equal to the reward received in the current time step, in time step t plus 1 plus gamma times gt plus 1, given that you start the state S. So again, this is basically equal to expected value of rt plus 1, given that st is equal to S plus gamma times expected value of gt plus 1, given that st is equal to S. And now again, we will take these two portions of the equation apart. We will solve them separately. And so for the first portion of the equation, let's write it down. The expected value of rt plus 1 given st is equal to S. Now this is basically equal to summation over all the rewards, the reward R multiplied by the probability of receiving this reward given that you start with the state S. And now we can clearly see that this P of R given S is not known to us, because the only thing known to us about our environment is the dynamics function, and that dynamics function can be given as the probability of landing in the state S prime and getting reward R, given that I was in the state S and I took the action A. So I need to somehow incorporate this action I take in the time step t, and this next state I land into in this as well. So let's do one thing. Let's again expand this, and I can write probability of getting reward R given the state S as a marginal probability, and so this can be expanded to summation over all the next states S prime and all the actions I can take. Probability of getting the reward R, landing in the state S prime and performing the action A, given I was in the state S. Now this is again not known to us, but we will make use of this somehow. So now note that this is basically the joint PDF of reward as well as S prime as well as A as well as S divided by the probability S. What we can do is we can multiply and divide by some same quantity, and we will still be satisfying the original equation. So let's do that, and we will be multiplying and dividing it by the joint PDF of the current state and the current action taken, right? And now let's just focus on this particular part, and this will basically make it equal to summation over all R summation over all the next states and actions, probability of going in the next state S prime and getting the reward R, given that we were in the state S and took action A, multiplied by now this particular term, and this will evaluate to probability of taking the action A given we were in the state S. So clearly this particular term is the policy term, and this is the dynamics of the environment, and both of them are basically known to us. So now we have solved the equation, and so we can say that this is equal to summation over all A policy pi summation over all the rewards and next states possible R times probability of landing in the state S prime R, given that we were in the state S and took action A. So this is the first part done, and the second part can be also solved like this. So the second part is basically expectation of gt plus 1 given that the previous state was equal to S. Right, so this is basically equal to summation over all g primes. So I'm calling the next return or the return for the next time step as g prime. So that will help us in differentiating between all the quantities of the current time step and the next time step. So this is g prime times the probability of getting this return g prime given that we are in the current state s. Now, of course, we are not aware of this quantity, and I want to somehow be able to convert this quantity into this dynamics function as well as the policy and so on. So, what's missing? Basically, everything is missing. We will incorporate the current state, the current action, the reward, and the next state in this, and we will do that by multiplying by taking the marginal concept again. So this will be g prime summation over all the possible next states, actions and rewards. So this is probability of getting a g prime given that we took the action a in the current time, in the previous time step, we got the reward, and we got in the next in the current state s prime given that we were in the state s in the previous time step. So this is all right. Now what we will do is we will open this up. This will be summation over all g primes, g prime times summation over s prime, a and r. This is the joint PDF of all of these variables. Divided by probability s. And so now what we can do is we can write this as summation over all the g primes, g prime, summation over all actions, rewards, s primes. Now I'm going to multiply and divide with the same quantity. And that quantity is going to be probability being in the state s, taking action a, getting reward r, landing in state s prime. And so now if you again consider this particular expression, so what this will evaluate to is a conditional probability. Probability of getting this return in the next time step given that we were in the state s, we took action a, we got the reward r, and we came in the next state s prime. Now this multiplied by this quantity is going to be equal to probability of taking the action a, getting the reward r, and landing in state s prime given I was in the state s already. Okay. Now if you see this particular term, we again have the same Markov property going on over here, that if I know this particular state s prime, then I don't need the information about my previous state, my previous action, and the reward I received in the t plus 1th time step, because this g prime only concerns itself with the rewards obtained from time step t plus 2 onwards, right? So we can simply say that this is equal to summation over all the g primes, g prime summation over the actions and rewards and s primes. This is probability of g prime given s prime times probability a, r, and s prime given s. Right. So now this particular term is again not known to us, so we will again treat this, and what we will do is basically summation over all g primes, s prime, probability g prime given s prime times, now if you treat this again and you open this up as a joint PDF, this would be a and r and s prime and s divided by probability of s, and you multiply and divide by the joint PDF of s and a, right? And so this will now evaluate to summation over actions, rewards, next states. It means as it is. Now this will become probability of going to the state S prime and getting the reward R given S and A, and this will be probability of choosing the action A given that you were in the in the state S. So again, this is essentially your policy. So I can write it like pi essentially. And now I essentially know this function. This is again the dynamics of the environment. This is also known. It is a policy of our agent. And now what we can do is we can do a very simple manipulation of the positions of these expressions. And we can write, this is basically summation over all the actions. Then summation over all the rewards and the next states, right? So probability of going in the state S prime and the reward R given S and A. This again summed over all the possible future returns, G prime times the probability of G prime given S prime. Now if you note carefully, this quantity over here is nothing but the state value function for the next state S prime, right? And so I can rewrite this as summation over all A and then this is V pi of S prime, right? So now we have again we have derived the two terms of the Bellman of the state value function, and so therefore we can now write the entire expression in a short form, and this will be summation over all the actions this will turn out to be common in both the terms. And what is not common is basically this R and gamma times this particular V pi of S prime. So this is R plus gamma times V sub pi S prime. So we have proven the Bellman equation for the state value function with the help of just simple mathematics, and we have not used the law of total expectations over here. Now we can similarly prove the Bellman equations for the state action pair value function as well. Thank you for watching the video.